Okay, this is the second clips for the lecture on the cable. The cable that we are interested in can be classified into two types. One is subjected to the concentrated or point load, and another one is this one, subjected to uniformly distributed load. What are the difference of them? The difference of them is based on the anchor, also the size of the cable. If the anchor is putting in cross position, so the force that's distributed from the girder along that anchor will act to the cable in the uniformly distributed load manner. However, if the force in the anchor are separate apart, then the cable is subjected to the concentrated load, as we learned it before. And talking about the cable, there is some important assumption that we supposed to do on this. First, the cable is flexible, okay, and it can be any shape. However, it is inextensible. That means the cable will subjected mostly to tension force. It acts like a two-force member. Okay, and the shape of the cable won't change much or change very negligible under the force. And I should add some more assumption since it related to the mechanics of material. The cable behave linearly elastic under the applied force, and plus it has small deformation that is related the inextensible cable. Okay, and also the material that's used to build the cable is a kind of steel or aluminum. Okay, that is going to be the homogeneous and isotopic material. Okay, now when we learn the cable subjected to the point load, we also have some note on the cable. Okay, the first note is the Tmax on the cable is occurred at zeta max. Okay, zeta max is the angle that the cable act with the horizontal axis. For example, for this cable, okay, you can see that the cable going to have the maximum angle here. So this point supposed to be the point of maximum tension. And second, all of the horizontal force, the T cos theta, if you have the cable and you have a force T here, is act theta here, so the component of this is a T cos theta is constant. Okay, is equal to each other everywhere. Now let us consider this bridge. This bridge is a model of a kind of Golden Gate bridge, and I'd like you to start to imagine how this bridge built. But for sure, this bit will built by the foundation, okay, under the soil here, and build the pier, okay. This pier gonna support the red column here that's built up, okay, to the sky on the left and also on the right. And then they also built the support here on the left and on the right, and they start by laying up this cable to this portion and fix it. Also this one, they put this cable into this position and fix it. Actually not fix it, it's pinned it, okay. They pin it at the top, and then they also lay the cable along this shape. It is going to be in a particular shape or parabolic shape, okay. And then they lay the anchor. This is a anchor. Since the anchor here is a lot, so the weight that will transfer from the girder to the cable will be uniformly distributed loads, okay, as we has discussed before. So then finally they built the bridge deck, okay, between the column and hang this bridge deck by the anchor. So the force from the very stiff bridge girder and bridge deck will transfer to the anchor, okay, and then from the anchor it will transfer to the cable, okay. This is for the cable, and from the cable to the support and to the column and to the foundation, okay. Okay, next, if you consider this cable, you may see this cable is a special one. They are symmetry, and when you start to analyze this cable, you got to find the lowest points of the cable and set that point to be the origin of the x and y axis, okay. And after that, when you get this axis, this is going to be the x and the y axis, okay. You will have also to know this h. This h is the sag, okay. This is sag of the cable, and this is going to be L. L is going to be the span of the cable. By doing this, if we just move from the origin O here to any point X here, and then we can measure here, this is going to be the Y, and later we will prove the cable equation. The cable equation gonna be in the form of y equal to anything x squared, and we can prove this is gonna be the distributed force divided by 2 times of the F sub h, and F sub h actually is the T cosine theta, is the horizontal force, okay. And after we have the cable equation, we can determine the tension in the cable, and also we can use the Tmax to design the cable later. Okay, let's talk about this slide. If the space between the anchor is small enough, the load from the bridge deck, okay, bridge deck, very stiff, very rigid bridge decks, transfer to the cable in the form of uniformly distributed load. I should mention this is supposed to be rigid, very stiff, Okay, and then in the analysis we set the lowest point at the origin of the xy axis, as I mentioned before. Okay, let us trying to derive the cable equation. To derive the cable equation, let us consider a portion of this cable having the lowest point at here. Okay, and set this one as the origin of the xy axis. This cable is subjected to the uniformly distributed load W sub dot, okay, and it's lie between this point and go up to the top here. And if we just consider this small portion of the cable, okay, this small portion of the cable also subjected to a small portion of W sub naught here, and it's gonna subjected to the force. If this one have the distance x from the origin and the small differential portion of this cable had the size of delta x, so the resultant for here is going to be W sub x, W sub naught times x. And also, if you may imagine, okay, the force that's act here will act parallel to this portion, you may say is T, and if you move it apart a little bit, there is also another force x as here is 3 plus delta T. Okay, and if this one is delta x, let's say this one will be delta y. Okay, if you zoom this portion of this cable up, okay, you get this portion of the cable in this shape. Now, if the force T has the angle here of theta, when the force T increased to 3 plus delta 3 due to the change of the force in the cable, we also have this one of theta plus delta T. So we cut the cable in the small segment. Okay, at this one is going to be what? It's going to be at distance x from the origin, and we have very small differential of, actually over here is the delta x. By doing this, we can apply the equation of equilibrium to this small portion of cable, and we can consider this equation to find some important aspect of cable. Let us first start by summation of x sub x equal to 0. If you set this at x sub x equal to 0, let us start by projecting the force in the horizontal. This one gonna be T cosine theta, and this one gonna be what? 3 plus delta 3 and time cosine theta plus delta theta. So we have only these two forces, and if we set this is positive, so this force is positive, this force is going to be negative, so we get negative T cos and positive this one. And the next one, summation of f sub y equal to 0. By doing this, you may get this one. This one is going to be T sine theta, and we also going to have for this one going to be T plus delta T, and then psi what? Psi delta plus delta, sorry, pi theta plus delta theta. This is theta plus delta theta. Okay, this is a small force 3 plus very small force 3 sine angle theta plus very small angle theta. And then we have up. This one is up, this one is plus. Okay, and this one going to be minus. So T sine theta is minus. And the resultant force also be minus. So this one is minus. The resultant force is minus plus this one, and then equal to 0. And then with summation of moment about point O, this one is point O to be the point of moment. And we will see this T sine gonna rotate like this. And this guy gonna rotate like this. Okay. However, the T cos gonna rotate like this. And what we have is the T cos gonna time this distance of delta y. Okay. And T sine gonna time the distance of delta x, and this force gonna time delta x divided by 2. So let's say if the counterclockwise rotation is positive, then this resultant force of the uniformly distributed load, okay, gonna time x delta x over 2 is positive, and the other gonna be negative of what? T cosine. Oh, sorry, T cosine is here. T cosine is here. T cosine rotates like this, and T cosine times delta y. And T sine here. T sine times delta x. Yeah. Okay, and we have this is positive. This is positive. This is positive. This is positive, and the last one is negative. And if we consider the delta x to be very small differential dx, and if we do that, okay, the first equation you may write minus t cosine theta, and you're gonna plus 3 cosine theta plus delta theta, and you're gonna have it for plus delta t times cosine theta plus delta theta and equal to 0. Since this delta x is really small, when it's really small and then you take the limit approach 0, you get the delta theta approach 0. So you may have this guy and this guy to be very small. And then you will have the rest of this. This is the force cosine theta. This is going to be the force in the horizontal direction, and the change of the delta is 0. Since you divide this term by delta x, so you may like this one to be d of t cosine. This will change. This is very small. It's going to reduce all this to this one, and with respect to x to be 0. Okay, the t cos theta, the change of the t cos theta is 0. So we get the differential of the t cos theta with respect to x is 0. That means what? That means all the force in the horizontal, okay, you may say all the force in the horizontal is a constant because the change is 0. So it is constant, and as you know, this is equal to f sub h. Okay, next we come into here. So this time we're going to have it for minus t sine theta. Okay, and Also, this one gonna be minus W delta X. Okay, and then we have plus 3 sine theta plus delta theta, and you have plus delta t sine theta plus delta theta, and then equal to 0. Since it's very small, you may cut this. Okay, and you may see that very small vertical force is going to be very small change in the vertical component of the cable. And if you divide this by delta x, okay, if you divide this again by delta x and this one by delta x, and let delta x cut and cut, okay, so this one will be the same thing. The chain of t and psi, this is very small, you can cut it, theta by dx gonna equal to the w, the minus gone, just move to the right. So this is going to be our second one. So you get this one and you get this one from the first two. What does this mean? This mean the component of the T force or the force in the horizontal, okay, is constant. No change, is no change. The slope is 0, is no change. You mean the slope is 0, is like this. It's just horizontal, okay, and the change of the vertical component of the tension will be the distributed load W. Okay, the last one. Since this delta x and delta x is very small, when it's time together, this can be eliminated. And then you may write this one gonna be t cos theta delta y equal to t sine theta delta x. Okay, and then you do again, it's going to be delta y by delta x equal to t sine theta by t cosine theta. If this is cut, this is going to be tan theta. And if it's very small, tan theta is going to be dy by dx. That is going to be the third relationship. Okay, let's take the first relationship, and then if you do the integration, as you may know, this is 0. When you like it, it's going to be dt cosine theta, and you integrate this, okay, and then like you integrate 0. So what you get is the t cosine equal to constant. That means the horizontal component of the tension are constant along the length of the cable. And the boundary condition, if you set this, you may get as x from A to B. That is going to be quite a constant. So actually, if you find this here at what? At cos 0. So you will get this at the f sub h. So what you get is t cosine theta equal to f sub h. Okay, and next, for the second equation, you do the integration. The same thing occur if you do some kind of dt sine theta equal to w dx, and then you do the integration. That is going to be the change of t sine theta going to be equal to this equation equal to W0 x plus constant of integration, and then the constant of the integration can be determined the boundary condition. Okay, and then at the boundary condition of x equal to 0, this one, there is no vertical force because the cable is only in tension. It is to force member. That's mean the component of force only in the horizontal, no vertical. And then if you put this, it's going to be T sine 0. T sine 0 is going to be 0. And also this one going to be 0. So C1 is 0. Then you get T sine theta equal to W x, the component of the tension, vertical component. Okay, equal to vertical load applied to the cable equal to the resultant of the uniformly distributed load. And okay, now we have here the T cos theta is f sub h, and as we have mentioned, all the component of horizontal force in the cable are equal. Okay, and then if you take this and divide them together, I mean if you put this one as the first equation and put this one as the second equation, you may like it's like a T sine theta divided by T cosine theta. It's going to be Wx divided by f sub h, and T cut T, and this is going to be tan theta. Okay, it's follow this. And by integration equation for y, that means after that you just say this is going to be dy equal to w naught x divided by f sub h and dx, and then if you do the integration, okay, you integrate dy, you get is y. Since the the coefficient over here w naught divided by f sub h is the constant, you can take it out and you will integrate for x dx. So it's going to be x squared and plus the coefficient of integration. And again, use the boundary condition. Okay, at the x equal to 0 and y equal to 0 here, you may say that is going to be 0 equal to this one 0. So the C2 equal to 0. We arrive at the cable equation, which is the parabolic equation. Okay, and actually this equation is enough to sufficient to solve this cable problem, but we can derive some equation for this cable to have the in-depth understand on it. Okay, let's say the horizontal force may be determined by using the boundary condition at x equal to L and y equal to h. That means we also have f sub h here. Okay, the f sub h here from this equation, the point here is x equal to L and y equal to h. So you just put this one as the L and put the y as the h. So it's h equal to w naught time divided by this and then L squared. You put the horizontal force up and put the sag down, you get this equation. And from this equation, you may take what, just put the equation of f sub h back to the equation, back to the Craven equation. You get the new form of cable equation, okay, in this form. Or you may find the cable equation from here, or you may find the cable equation from here. You're going to get the same line of cable, okay. And the horizontal force, this is very important equation. This is very important equation. Because of what? Because actually the F sub h can be determined, okay, easily. And if you know F sub h, because it's a constant, okay, across the cable, you can find any tension of the cable with respect to the cos theta. If we know this theta, we can find the tension in any point of cable. And if you may recall, we have y equal to the cable equation, W divided by 2 f sub h, and then x squared, and then dy by dx is equal to w divided by f sub h and x, okay. And this is going to be the tan theta. If you determine the theta from this equation for any given x, you may determine the tension in the cable later, okay. And the Tmax also, okay, can be occur at the minimum or the maximum theta. What is called is Tmax occur when the theta over here is maximum. And what we have is what? The cos theta is minimum when the theta approaches 0. If you may recall, if 0 degree, okay, cos 0 degree, or 0 degree equal to what? Cos 90 degree equal to what? Cos 90 degree, if it's close to 90 degree, it's going to be 0 degree, 0, okay? This is going to be 1. So when the cos of the theta is large, cos theta is minimum, or when theta is approached, yes, this is going to be close to 0. When cos close to 90, this value close to 0. So when this close to 0 is going to produce maximum T. That's correct. Okay. In this cable, okay, it will occur here, and then we have T max of F sub h square plus WL square, and then if you push the F sub h into that equation again, and then we do the calculation, we will have the equation for T max in this form. Just only use the dimension of the cable and then time W naught. I mean, I should mention again, you don't need to remember this kind of equation. We can use the cable equation, and we can rearrange the method of calculation, and we also get the T max. Okay, it should be noted one thing: when the cable is supported by the uniformly distributed load, and then you get the equation of this. This is a kind of parabolic equation, okay, parabolic equation. However, when we have the cable such as the cable between two electrical poles that's used to transmit electrics to our house, those kind of cable subjected mostly to their own weight, okay. When it's subjected to their own weight, it's going to have the catenary shape, which is the shape between the parabola and circular. is not studied in this chapter. I recommend you guys, if you have chance to work with electrical company, you may open the engineering static book and take a look at this. Okay, but when the ratio of the sag, okay, and the span is so small, that means the sag is going to be the h here, and the span is going to be the L here. When the ratio of H and L is small, okay, you may use the cable equation of this case to analyze this candidate cable. Okay. Okay, for the length of the cable, you know from the previous discussion that this is going to be very small vertical distance. This is going to be very small vertical horizontal, and then the length of the cable can be determined by this. If you do this by ds by dx, you have this one by square root dx square divided by dy square. Since this one by dx, that means this one going to divide by x. So when you take the x in, that is going to be this one, okay, and this one going to be what? This one going to be 1 is cut, and plus dy by dx and then square. You will get the same equation here. Okay, if you like. You just realize this, you get this equation, right? And then you just move the dx and time it. Okay, and by doing this, coming into this cable equation in the form of dimension of the cable, and then you do the differential equation, you dip this. When you do the differential of this, you do the dy by dx is going to be h over l square and time 2x. Okay, and it's going to be 2hxl square. You put it over there and you rearrange it. You can determine the length of the cable in this form. Okay, there are many kinds of cable. Okay, one that we are interested in here is going to be statically determinate cable. And we also can determine this for this one at the end of this lecture. If you like, you may study by yourself. And for this B, this cable is statically indeterminate. We cannot analyze this cable by using our free body diagram and only the equation of equilibrium. We need like a compatibility equation to help to solve this. And that is going to be in the advanced courses. Okay, and now, okay, the cable is subjected to uniform load. Let me conclude it. First, the cable equation are the parabolic equation, and it have the equation in the form like this. And this form of equation only obtained when the coordinate set like this. Okay, coordinate set origin as the lowest point of the cable. And also we have these two equations. The second one to determine the zeta, which is important if you like to find the tension at any point of cable. So to find the tension force in any point of cable, you got to determine the zeta at that point. Okay, and note the horizontal component of tension and reaction are equal. You know, f sub h always equal. Is this constant? The maximum tension of cable occur when the cable have the maximum angle with the horizontal line, largest angle, or have the maximum angle. Okay, there are three types of problem now, and our three example gonna follow that. First, we will find the Tmax in the cable. Okay, when we find the Tmax, we're going to know the applied force. And then after we find the Tmax, we also can design the cable by using the allowable normal stress. Okay, or we can check if the cable is big enough or not by check it with the allowable normal stress. So the Tmax have two things. One, we use Tmax for the design to find the size of the cable. Another one to check sufficiency or ability of the cable to resist the giving force. Okay, check the cable for check if the cable is large enough to resist applied force. Okay, and the second one to determine the allowable maximum force that can be applied to the cable. In this way, they're going to give you the T allow. Okay, that is the maximum allowable stress. Usually, the T allow is going to be the T max of the cable. Okay, and then time factor of safety. And this T max can compute easily if you have stress equal to T over A. So the T equal to sigma A. So the T max can be sigma allow times the area and then divided by factor of safety. Okay, the sigma allow may be 100 megapascal. The area of cable may be 100 millimeter, and factor of safety may be 2. You can find the T allow example. And the last one, determine the cable length and sag when the allowable force or allowable stress are given, and also the applied load are given. And then let's start the example that we have. Okay, let's first start by this one. This is the cable having the pin at A and pin at B, and Hank allow A and B have the stiff, very stiff girder subjected to the W of 12 kilonewton per meter. And this cable have the minimum height allowed here. So if we like to analyze this cable first, we set this the x-axis, and we also set this as the y-axis. And by doing that, if we like to determine the y, the y is going to be w sub naught divided 2 times f sub h and then x squared. To use this equation, we got to determine the f sub h. Okay, to be able to find x sub h, you're going to determine this distance, which is the location of the origin of the coordinate. Okay, and then if you write down the cable equation later on, you can determine the tension in the cable at anywhere by using the equation that you know is T equal to f sub h and then cosine theta. Okay, let's start by putting the axis here, and let the distance from the y to the b is x, and then the distance from the y-axis to the a gonna be here is gonna be 5 minus x, and then from the cable equation we will find the x first by using the coordinate at A and B. Let's start by at B. B, if you see, we're gonna have the coordinate of what? The coordinate, you can move from here, and then here is x, and here is 3. So the coordinate is x and 3. So you put 3 for the y, and equal to w to f sub h, and then x squared, because we don't know x yet. And for the a, okay, the coordinate of the a, you're going to move here for 5 minus x. And since you move it in negative direction, so it's have a negative 5 minus x. And then you go up for 2. So the coordinate here is minus of 5 minus x and 2. And then this is going to be the y. So put the 2 here. And since this one is x and then square, so take the negative out. And you may can see that this and this is going to same. So this is going to 3 over x squared equal to 12 divided by this. And this one going to be 2 over 5 minus x squared equal to 12 to f sub h. And since these two is equal, you may get the equation of 3 divided by x squared equal to 2 divided by 5 minus x and then square. And then if you move across, this is going to 3 times 5 minus x square equal to, this is going to 2x squared. And then you get 3 times, this is 25 times 5. This is times 5 and then x and then plus x squared and then equal to, this one is 2x squared. So you get this. This is going to be 25 minus, this is 10 is 30x, and then this is going to be plus 3x squared equal to 2x squared. Okay, if you move this one here, it's going to be x squared minus 30x and plus 75 equal to 0. And then you can determine x from what you have. Okay, if you have the equation of ax squared, okay, plus bx plus c equal to 0, you may find x from this equation. And then you solve the equation, and then you get this x equal to 2.753 meter. Now, this is going to be 2.753, and then you will get this. Okay, 5 minutes 2.753. Okay, now, not now here. You may put this value to determine the x sub h. Put this one. You may put this one. Plug this one back here. Okay, and then the equation will give you the f sub h. The same thing here. Just put the location. You get this one for 15.15. And then when you get this one 15.15, now you plug it in here, and you know this is for 12, so you can write the cable equation in the form of this. Okay, and also if you like, you may put this one for what, 12, this is going to be 6 divided by 15.6 divided by 15.15 is going to be 0.39. Sorry for this. This one can be 0.39604 if you like. And then if you dip it, you're going to times it by 2. It's going to be 0.792. So this is going to be uses to determine the angle of the cable with respect to the horizontal line. Okay, at point B. At B is here. As B, we have the x of 2.753. So that's B, x as B equal to 2.753. If you plug into here, you may have theta sub B equal to inverse tan of 0.792 times 2.753, and then you get the angle at point B. That means you get this angle, okay, and then you get the angle of 65.35, and then you have the equation of what, as I mentioned before, the t equal to f sub h, you know that, and then cosine theta. If you find S sub b, this is going to be theta sub b, and then you get it for 36.33. And now SA, you may find the T sub A. T sub A going to be f sub h divided by cosine theta sub A. And A is what? A is the distance that's going to be measured from this one to this one, and then the A is 5 from x equal to 5 minus 2.753, and then you put it into here, you got this, and this is going to be theta A, and then you put theta A here, you got the T sub A, and T sub A is less than T sub B because the angle here is theta sub A. The angle here is theta sub B. Theta sub B larger than T theta sub A. So theta sub B also larger than T sub A. And we get the T sub B, the maximum. And T sub B gonna use to decide to find the size of the cable. Okay, T min is going to be what? T always going to be f sub h. Okay, the T min for this case, you have the lowest point at the zero slope. Okay, and how will you decide the cable? Mechanics of material, you can decide it. Next, we are going to determine the W this time. We are going to find the W. It's going to be what? When it's said the allowable tensile force is 16 kilonewton, that is going to be T allowed. And to make sure you understand it, you have sigma equal to T over A, and then T equal to sigma A. And by doing this, you may have T allowed. It's going to be sigma allowed times A. Okay, that is going to be not. From the T allowed, when you have this, you may have like specify some sigma allowed and A, and then you also know that the sigma allowed is going to be sigma supply of the steel divided by some factor of safety. So that means you can also specify the sigma allowed by the equation that you have for the mechanics of material, right? Okay, and then start by the same thing, put the origin at the lowest point of the cable, and then what you have is x is here and phi of x is here, the same as before, and from the cable equation you're going to use the coordinate at A and B to determine the x, and again at the B has the coordinate of x and 3 is going to be x is here, x is horizontal and y is vertical. You put the y 3 here and x still there. Okay, as the A, again you move here, that's going to be 5 minus x. Since it's in negative direction, it's going to be minus of 5 minus x. And go vertical for 2 meters, so you get 2 equal to this guy, and then 5 minus x squared. The same thing that we have before, this one and this one, they are equal. So you just put them together as the previous example, and then you get the same x. Now the verb is changed. We are looking for what? We are looking for this one. Okay, look for this one, and from this we need to move the horizontal force up and put the y back here, so we arrive here. And what we have is the coordinate of x and y. Since we have the coordinate of x and y, we can write a more simple horizontal force equation. At the b, we have this of what? Of 1.26 t w sub naught. Okay, we have here because the t max is here. So we're going to go further. The t max occur at b. That's the cable equation that we have. We have the slope of this. So zeta max is occur when the x is going to be the 2.753. Okay, and then we have this 2.75 tw and divided by f sub h, and then when you cut this and this, okay, you can get the number and you get the zeta max at 65.36. Now coming into this important equation again, now you got the zeta max, okay, of this, and you also have the t max to be the t allow, right? So you put everything together, you get the value of 5.38 kilonewton per meter. So that is quite simple. Just do some kind of manipulation what you are looking for, and for this comparison between problem 1 and problem 2, you can see the geometric analysis to determine x, to determine the position of the origin of the xy axis. That is the distance x is the same. Okay, that is the end of chapter. Oh, sorry, the end of example 2. Next, example 3. Example 3 is another way of thinking. They like us to determine the sag. Okay, sometimes the sag distance is important because if it is too much, okay, it will make the cable can sideway easily. Okay, and then the sag also depend on the applied force, this one of 500 Newton per meter, and the maximum allowable force that can be the maximum force here at A and B. Since this cable is symmetry, so the T max gonna occur at A and at B. So we start by putting the origin here at the middle and put this one as 0 point. Now for the equation, for the cable equation as before, we start to find the slope equation, and now at the support B. Support B is here. That is going to be half of the span, that's going to be 15, and then up h. So this is the coordinate of support B, and by this coordinate you just put into the cable equation, and it's going to be y, okay, this is going to be this one, and then x squared. You still know x sub h. And then the equation change to the horizontal force equal to 2 to the 50 divided by h and times 15 squared. This is the equation that's determine the constant horizontal force. And next, the Tmax occur, like I said, Tmax occur at the B or at the A. Now we select the B, since it's in the first quadrant of the xy coordinate, and it's occur at x equal to 50. So from the equation, that we have is going to be the angle theta. Okay, it's going to be W sub times x divided by f sub h. So you say this is going to be f sub h. Okay, it's come from this equation. And then what you have is you have this as the equation of theta max. And what it means is it's going to be like this. So by doing this, what we have is going to have what? This is the cable, and this is horizontal line. Okay, and what you have is the theta here. That is the point B. This is the point B, and then you have this ratio. So you have this one and this one. So you have what? This one of the ratio of what? Of 1. This one should be 1, and this one is 0.1333 h. See, this is your B, right? This is your angle. This is your angle. Okay, and then you have this one of this, and this is going to be y divided by x. So this is the y, and divided x equal to 1. And if you're going to find the cosine of it, it's going to be this is going to be square root of what? Of 1 square plus 0.1333 h square. So the cosine is going to be this divided by this, and then you get this, and you put into your equation the f sub h divided by cosine theta max. By doing that, you have the theta max, okay, of this, and f sub h, you got the equation already. This is f sub h. When you divide it, you just use only this part times it, and then you solve for it for 8 meters. Okay, that is going to be the problem example number 3. And then what we reviewed it, the first one, what we have, we find the Tmax, right? And the second one, we find the applied force. For the Tmax, we know applied force. For finding the applied force, they give us the T allowed, which is going to be the Tmax. And the third, we find the geometry of the cable. And we also have example that I like you guys to go through all of that. It's not that hard from the basic you have. We can analyze this kind of cable and thus they work in combination. Okay, in this way the cable will helping the task in resisting the force. And what we have for the examination is 3 types of problem that I mentioned before. Actually, I supposed to pick only one, but you guys supposed to know all. Okay, for the rest of PowerPoint, I just assign you if you are interested or you are available, or in the future if you work on this kind of problem, you may come and study more. Okay, let me end the example for the cable here. I still have to demonstrate you by writing the example to explain you step by step. That's supposed to be more clearer than from the PowerPoint. Okay, now I should finish it here. Bye.